Hey there! Today we're going to talk about energy. Energy is extremely important in biological systems because nothing happens without energy. Okay, so you probably think you have learned about different types of energy before, but I have a whole system of classification that's probably going to be a little different than what you've seen. So let's talk about this. So let's start with energy as a whole. So energy is my top spot, and energy gets broken down into a number of different categories. Now, energy is important that we think about it in categories, mostly because of thermodynamics. So, the first law of thermodynamics. First law of thermodynamics essentially states that all energy in the universe remains the same. So, essentially, energy cannot be created or destroyed. Now, we know that if you push into certain realms of physics, there are some ways to do some things with energy that are more complicated than this. But from a biological perspective, we're pretty much talking about the energy that makes its way to the Earth and the energy that we are actually capable of harnessing in some manner. So, first law of thermodynamics applies to the majority of biological systems on this planet. Everything else you can take up with, physicists or something. But essentially, it says that energy is constant, or at least total energy is constant. So total energy is constant. Energy cannot be created or destroyed. But it can be transferred between forms. So this is stated slightly differently in every version that you'll see it, but this is the way I like to think about it. All right, so that's the first law of thermodynamics. So therefore, if it can be transferred between forms, what we care about are the different forms of energy. So you've probably heard of two major categories of energy, and this is how I start the classification. Energy can either be kinetic or energy can be potential. Kinetic or potential. So kinetic is the energy of motion, so that's something that is moving, and potential is the energy of something essentially waiting in some form. So we'll talk about what that means in a moment. So kinetic energy is movement, potential energy is waiting or stored. Sometimes we call it stored. All right. So I'm going to start with the kinetic energies because there's a whole bunch of things that we actually would fall into the category of kinetic energy. If kinetic energy is the energy of movement, then anytime we get energy from something moving, then it's got to be kinetic. So here's a bunch of the different ones that we will talk about. We've got actual physical movement. So sometimes we talk about things at a large scale. Large scale means an entire object in some cases, or an entire organism, or really anything just physically moving. So this could even be small things, but as long as the thing creating the energy is the movement of that item from one place to another, I'm going to call it physical movement. Sometimes we're talking about the movement of specific things. If we're talking about the movement of molecules, there's a couple of different ways we think about them in terms of energy. So there's molecule sort of vibrations, and when molecules vibrate in certain ways, they make sound. Sound has its own energy. It is the vibration of some molecules. So we've got sound. The other thing that molecules do is instead of just vibrating, they kind of shake, I suppose is the best way to think about it, but they're constantly in some form of low-level motion. That's the energy of heat. The amount that the molecules are moving is how we consider the measurement of heat. We can get even smaller and talk not just about the molecules, but about electrons. If we talk about the movement of electrons, that's a movement of charge. Any kind of charged movement is going to be what we call electrical energy. So that one's going to come back a surprising amount. And then finally, the last kind of kinetic energy that ends up being somewhat important to us as biologists is the energy of the movement of something even smaller in case than electrons, which is of photons, and that is the movement that we call light. So the movement of photons is what ends up creating light. So each of these is its own form of kinetic energy. And I'll go through them one more time just so we can remember what it is that we're trying to move in each case. So in the case of physical, we are trying to move objects, could be organisms, or, well, in the case of biology, a lot of times the physical can be literally a molecule that has to move from one place to another. So really physical movement is from one place to another. So that's what's going to be the key about physical movement. And what makes that different from, for example, sound movement is this is essentially vibration of molecules. So vibration of molecules is sound movement. I think molecules is actually longer than vibration. Heat is the movement of molecules. So movement of molecules is heat. Gotta be able to type to make this work. And it's not quite the same as sort of the waved vibration that we think of as sound. That's something sort of moving up and then moving down. But in this case, it is the singular motion where they're just doing their own little moving thing. And that's what we measure as heat. Electrical is the movement of charge, which is often the movement of electrons. So it could also be the movement of something positive because it's charged, but it's still electrons. And then light is the movement of photons, which they get very complicated, and that becomes a whole physics thing as well. But from our perspective, that's what's important about this. So movement from one place to another, physical. Vibration or sort of wave-like movement of molecules is sound. The sort of generalized movement of molecules is heat. Movement of charge or electrons is electrical, and movement of photons is light. All right, so that takes us to potential. Now, I only really break potential into two things, but then I'm going to break one of those into yet another thing. So from our potential energy, there are two things. One of them is what we would call positional. And I'll get back to that one in a moment, but it's the one that you tend to think of as like the diver on the diving board type of thing. And then the other one, which is extremely important for biology, is chemical, or the energy bound up in chemical bonds, or the energy released when you break one. So this is stored energy. It's energy that would be electrical, but those electrons are not moving yet. So it's how much energy when they actually shift from one place to another. So chemical is stored in chemical bonds. And this is typically related to electrons, electron positioning, and things like that. And that will come up again. All right. And I said that I was going to break one of these down one more time. So I am indeed planning on doing that. The positional energy from a biological standpoint breaks down once more. On one side, I'm going to call it gravity. So position related to gravity is important because the further you are away from the gravity, the more you want to come back towards gravity. So this is the movement we think of in terms of that diver on the diving board or holding something in the air. It's holding energy that the moment it's let go, it moves towards gravity. So a gravitational pull or distance from the gravity. And of course, to a certain point, this increases as the gravitational pull is large, but as you get further and further away from the gravitational pull, it could decrease. The other one, and this one becomes more important for biology, would be positional in terms of gradient. So that essentially means how much you have, or is there a lot on one side versus another? And so in terms of gradient, this is stored energy that is more related to how bunched up things are. So if they're positioned all close together, they're likely to spread out. So related to concentration more than anything else in terms of biology. All right. These are all the types of energy that we may encounter and the types of energy that convert from one to another, which is what makes them important. So as we move through different aspects of biology, we're going to actually watch how this happens. So for instance, light movement of photons is a big deal because it provides a large chunk of energy for this planet. When those photons come down, they hit plants. When they hit plants, they cause electrons to start to move. Now we have an electrical energy. When the electrons move, they cause chemical bonds to break and or reform. That changes the structure of molecules. They might cause something to move from one place to another. That creates and moves more energy. So now, if this is all true, we do have one problem with the conversion factor of energy, which is that converting energy from one place to another is complex and difficult, and oftentimes results in some changes. And this is where the second law of thermodynamics gets involved. Let me make that big again. So, our second law of thermodynamics essentially tells us that although energy is constant, that energy transitions or energy changes, transformations, actually let's call them transformations. Energy transformation includes some energy transferred to heat. That's really the important part, is that whenever you transfer energy, it involves molecules getting jostled in some manner, or at least something moving. Therefore, some of that energy in any of these switches gets transferred to heat, and heat energy is the hardest one to capture. So we often think of this as energy loss. Now you would say, oh, first law of thermodynamics, it can't be lost. It's not lost. It's just lost to the fact that doing any of these changes causes the molecules to go, oh my God, what? And they get a little bit of the energy from that they can't reharness. And that's sort of the important part. Transferred to heat or lost from use. Okay, now this takes yet another important step though. Because what it does is, anytime we do that, it gets things moving. So again, heat is movement of molecules. It increases the movement in the system. And we also say that increases the chaos or entropy of the system. So anytime we switch from one to another, we should have an anticipation that there's going to be some difficulties with heat or energy or entropy that we need to deal with. So the first law says we can transfer this energy around, but the second law says it's not going to be easy to do, and there's going to have to be some considerations. Either you're going to need to input more energy to control for that heat loss, to control for the entropy, or when you do this, you're just going to lose some, and it's going to become entropic, and that's the way life is. So all of this comes together in the building and structure of biological systems, and especially biological metabolism. So now you have all of this sorted out and in front of you. So the next time you deal with something energetic, you can bring this back and say, well, I can nail down these types of energy and see how this whole process works. So I hope that will be helpful when examining some equations in the future, or anytime you're looking at anything biological. All right, thanks.